Let me restart the session 4. Again, the first speaker is Van. Now Van is talking about modeling ILRS barometric accuracies using the Vienna mapping function, VMF.
Hello again. So my talk is on monitoring ILRS barometric accuracies using the Vienna mapping function for optical wavelengths. Over here on the left is a chart of the impact of a 0.1 hectopascal error on the tropospheric correction as a function of elevation angle. So here's 90 degrees, here's 10 degrees, and Yvonne in 2015 derived a requirement for the ILRS based on the GGOS requirement of the reference frame accuracy. He derived a requirement saying every SLR component should be calibrated to sub-millimeter accuracies. So to eliminate barometric pressure to reduce the barometric error to the sub-millimeter accuracy requires that we have pressures accurate to 0.1 hectopascals or 0.1 millibars. The bad thing about a barometric error is you're not going to, if there's a barometric error, it's not going to impact data precision. It's not going to affect the single shot RMS. It's not going to affect the neural point RMS. It's not going to affect your calibration RMS, but it will impact your data accuracy. Solving for only range bias is not going to remove all the systematics due to tropospheric bias. Christoph has shown this. And odd model tropospheric biases will negatively impact your station height, if not modeled. The Vienna mapping function for optical wavelengths, there's links here to where you can get the data on the web. And there's 3 flavors of the VMF. There's this flavor here, which was parameters based on ray tracing delays used in the European Center for Medium Range Weather Forecast, ERA interim numerical weather model data, a climate reanalysis. And the time span of this data is January 1990 to August 31, 2019. And then there's another flavor that's forecasted using numerical weather models. And there's a third type of operational numerical weather models. Data is available the next day. And the time span of this is January 1, 2008 to the present. So I compared this data, this flavor of data, to this flavor of data for the time in common between the 2 data sets. And then I also compared this data to the barometric data from a number of our stations in the ILRS network. So here's a comparison of the 2 of the flavors, the EL versus the OP, by station. So you can pick your favorite station over here on this table on the right. So these are the differences in hectopascals between these 2 data sets when I aggregate the data over this 12-year time span between these 2 VMF. And most of the differences are less than 0.2 hectopascals. So on this chart here, I plotted over here on the left is the pressure differences. So the VMF data occurs every 6 hours. So we aggregated the barometric pressures from our sites every 6 hours from all satellites. And so each blue dot here represents a common 6-hour difference between the VMF and what the station measured as far as barometric pressure. And then the red line is a running average. This site here is Haleakala, the old station, 7210. And you notice here that all of a sudden looks like the barometric pressures from the stations increased in value, and that actually had an impact on the station coordinates over here. And after this discontinuity was sort of fixed, it looks like the sensor was drifting, and the on-station barometer is actually drifting, which you'll notice the heights were also drifting here, because in ILRS 2020, only a range bias was estimated. There's no tropospheric bias that was modeled. So here's station 7839 Gratz from 1992 to up until the end of the VMF, which ended in August 2019. So over here is, here again, the blue dots, each blue dot is a 6-hour difference between the two, between the station's barometer and the actual VMF. And then over here on the right, so on this chart, there's a discontinuity when when they changed the barometer to a parascientific MET 3. Happened right here, and you can see there's this discontinuity in the data. And in ILRS 2020, they're estimating a range bias, which I think the analysts didn't know what was causing a range bias in this period here. And over here on the right, I aggregated the data, these differences versus year. And I also, I did pressure, and you can see that in 2015, the barometer started to drift again, which Gratz resupplied all the data to correct this drift in the barometer from 2015 to the end of 2020. And also plotted temperature differences to see how well temperatures compared. So that's this red line here over time. And here's two additional stations. Two of these are NASA stations. Here's McDonald on the left, 7080. For some reason, when they changed the operating system, there was a jump in the on-site barometer, and then there was another jump down here. I think this was documented in a data handling file. I'm not sure if this was documented in an existing data handling file. And then there's another, seems like there's another discontinuity here, or change, which I don't think this is documented. And this green line is when they installed a parascientific MET 3. Prior to that, they were using a Cetra barometer. Over here on the right is Yargadi 7090. And the different lines here is when they installed, when they updated their barometers. So the red line seems to indicate there wasn't too much variation in the pressure versus the VMF. So there's no obvious discontinuities. But there was a, oops, sorry. In the case of Yargadi, there was a 0.5 millibar mean offset between the station and the VMF. And since they changed barometers multiple times, which were calibrated to NIST, I think this 0.5 millibar error is in the VMF and not in the station's barometer. And then I looked at seasonal pressure variations as a function of temperature. So I aggregated these differences by month and then plotted them on the left axis. The blue bars are the differences by month between the VMF and the on-station barometer. And on the right axis, I plotted the temperature for that given, the average temperature for that given month. So there seems to be a correlation between temperature and the VMF differences with our on-site barometers. Over here on the right chart is Yargadi. So temperature is on the right axis in gray. Yargadi doesn't have as much temperature variations because they're out in it's like a desert-like environment, which has very good weather. And their pressure variations don't vary quite as much as a function of temperature as the station Gratz. So then I took the mean pressure differences between station minus VMF And this is a summary of some of the best high-performing systems in our network. So the NASA stations are here on the left side of the, and the over here on the right are mostly stations from EURLAS. So you can tell on this chart that there's some significant differences, more than 1/10 of a millibar, between the on-site barometer and the VMF. So what might be causing these errors? So the potential error sources are, well, the barometric sensor, either stations could be off, the ray tracing technique may not be perfect, and the station height used in the VMF may be a potential error source. And the on-modeled height errors between the barometer sensor and the system reference point could also be an error source. At some of our stations, the barometer is not the same height as the system reference point, so that needs to be modeled in the on-site data processing. If it's not, you're going to induce a small error in your barometric measurements. So, like I said, again, we need to reduce these barometric systematic errors to the sub-millimeter level. To reduce this to the sub-millimeter level, we require absolute pressure accuracies of 0.1 to 0.5 millibars, depending on how low the stations track, on the lowest elevation angles. And station heights in the VMF need to be accurate to better than 1 meter to keep the uncertainty in the barometric pressures to less than 0.1 millibars. So over here on the right is the same chart as the last slide, but I added here on the table on the left are the, I queried the people who generated the VMF to ask, what heights are you actually using in your analysis? And they're actually using the heights, the approximate heights from the ILRS site eccentricity file. So this column here are the use of the different stations. These are NASA stations here and non-NASA stations over here. The NASA stations all sit on top of a monument, and the system reference point is 2 to 3 meters above their monuments. So in this ILRS site eccentricity file, the approximate heights are based on the NASA monument, not on the system reference point. So that's why you see the differences in station. So I did this difference. This is VMF minus the station heights from I2F 2014. So some stations, the station height is off by 2.5 meters. In the case of TLRS4 at 7119, the height in the eccentricity file is way off. It's off by 9.6 meters. So over here on the right are the yellow area is the NASA systems and the European systems over here on the right. And the green bar is now when I model the height difference in the VMF. And in most cases, when I model this height difference, is the differences between the VMF and the station barometer, the differences usually decrease. And I got this information from the site logs. So here's some notable height differences between the system reference point and the barometric sensor based on the site log. And then I added a column. So here's the differences in meters for these stations here between where the barometric pressure was measured versus the system reference point. And over here on the right was this modeled in the on-site processing? So there's a bunch of question marks. I don't know if some of these stations modeled this height difference or not. So on this chart here is I normalized these pressure differences after removing some systematic differences between the stations and plotted by year the mean bias between the VMF and the station barometers versus time over here in this chart. And these are the different stations. These are some of the high performing stations these are some of the core stations used in I3F 2020. Over here on the right is the SLR scale from I2F 2020. And you can tell over time, as better barometers get installed in the network, has a positive influence on our scale. So I think barometric errors may had some influence why our scale in 1997 seems to be skewed low compared to data after 1997. So this is the last slide. So there are systematic differences between these two flavors that are site-specific. On average, over 12 years, these for all sites are less than 0.4 hectopascals. The VMF for optical wavelength uses approximate heights from the eccentricity file, but any errors in this can be accurately modeled. After modeling any VMF height errors, there are still site-specific systematic differences between this one flavor and the SLR barometric pressures up to a few tenths of hectopascals, but I think they're consistent over time, so that can be modeled also. So the VMS is very good at detecting drifts or discontinuities in our SLR barometers and can be used to model historical barometric errors. And the proliferation of more accurate MET sensors in our network, beginning in the late 1990s, had a positive impact on our SLR data quality and our SLR scale. So the last, here's a couple of recommendations. Perform yearly barometric calibration with a known standard and report results in your station history log. Also in section 12.01 of the site log, you should add some additional information. If the height difference between your sensor and intersection is not zero, document any adjustments made to your barometric measures to account for this height difference. Thank you.
Thank you, Van. Very important error source in today's data. Do you have any questions or comments? Yeah, only a short question will be allowed. If not, yeah.
So if there is any drift or discontinuity in your pressure measurement, can VMF be
Yes.
used to correct
Yes.
the data?
Yes.
Or should we really correct the data or just leave it
Well,
as
we should document in the data handling file how to fix the data. That's my recommendation.
Okay, thank you.